Well, it's 8:30. Hello and good morning. Thank you for joining us this morning for our fourth webinar, which is titled 7 Reasons You Should Consider Continuous Chromatography to Intensify Your Bioprocess. So I really wanted to thank you all for joining this morning. I know it takes something to be at a webinar and create the space in your calendar to join an event like this, which takes a certain amount of your time. And so I wanted to thank you for doing that. I also wanted to let you know that it's my commitment that you get something of value from your time this morning, because I know your time is precious. And we'll just wait another minute or two for additional people to join. So this is being shown through 2 platforms. You guys have joined on Zoom, but it is also being broadcast on LinkedIn. So, and those participants, of which I believe there are 80% of participants or something, you will not get to see on Zoom, okay? So anyways, thank you very much. We will wait another minute and then we will get started. And just by way, and the webinar is about an hour. We will attempt to finish in about 45 minutes and leave some time for questions. And should you feel that you have questions that may be confidential, then, please send us an email. And, if it's a simple question, you can put it in the chat. If it's you want to have a more detailed discussion, then we can certainly do a one-on-one and schedule another time with you or your team members or associates, and perhaps even sign a CDA if necessary. Okay. So with that said, I will get started. So we've heard a lot about continuous chromatography over the years. And while it all sounds like a good idea, of course, if big companies that make, cookies, for instance, were to make those one at a time, they'd all go out of business. So, whether it's juices or milk, milk cartons, etc., these things are all done in continuous processing. And we are all aware that continuous processing reduces cost, brings about efficiency. But then we live in a regulated industry where everything has been batch oriented. And even though small molecule production has moved into more and more into continuous processing, in biopharma, this has been far and few between, where only a few processes are now starting to get scaled up into continuous processing. But there are major economic drivers, there are major operational reasons, and we'll go through those starting now. So first, we have launched a series of webinars on various topics related to smart processing or process intensification. And for some of you who are joining us for the first time, your question might be more fundamental, like, who are these guys? Who's Seprogen? I don't know anything about them. So before I launch into continuous processing, I'll just give you, for the sake of a background, and for others who know us, please bear with us. I have a couple of slides. So we are a company that's 35 years old. We are an innovator in this field of bioprocessing equipment, technologies, and materials. We have over 200 global installations, about 30 plus FDA approved drugs. And we also provided some key enabling equipment for processing of 2 major commercially available COVID vaccines. So there are probably 100 million plus people walking around with vaccines in their arms that might have gone through our equipment. Okay. So yes, we know something about GMP manufacturing. And there's probably over $20 billion worth of biological drugs and vaccines being made using our equipment. And we are inventors of radial flow chromatography. Some of you who have been in the industry a long time may know that. These are very much, for others, they may be new, but they are proven technologies, and they enable high throughput at low pressures. We have ion exchange resins, we have column packing systems, a whole line of chromatography systems from the bench to large scale, single-use systems with disposable flow paths, continuous systems, inline buffer blending, dilution, and buffer blending systems. The two are very distinct. Dilution is making a buffer, concentrated buffer, and diluting it, and buffer blending is making it from stock chemicals, making the buffers. And then we'll address something today, which is our DSP systems, which is chrome combined with buffer blending. Okay, so it all happens in one system, and it happens transparently behind the scenes. And then continuous systems in stock, inline stock buffer blending. And just slides on, something here about large scale column installations, small bench systems, single use systems, continuous systems, resins, pre-packed columns, inline dilution systems, continuous systems like that. Okay. So that's the 1 minute commercial. We are done. And so now what is the problem with the current process? Okay. Everyone is focused on reducing cost, reducing the complexities, speeding up the process, reducing cycle times, reducing FTEs, operating costs, cost of goods, cap cost, etc. So historically, biological manufacturing processes have been batch or fed batch, right? And this has resulted in very complex processes, which are unit operations dependent. So you have a whole series of unit operations and hold steps between these unit operations. And so everything's labor intensive. You have to take samples at each point in the process, creating hold steps, and it adds to the cycle times, lowers the costs, etc. Right? And then the facilities that we have been modeled after this batch process. So if the titers go up, then suddenly the purification suite is not big enough to handle those large columns or skids, or our buffer suites don't have the capacity to make buffers, or we don't have enough storage space for those things. So lots of issues like that, where we are blocked in terms of ability to really bring efficiency to the production floor. Well, one of the most compelling reasons, since we are a regulated industry, when people talk about continuous chromatography, one thing may come to mind is, gee, what does the FDA think about it? So we wanted to get that out of the way. For people who are not in the know, the FDA issued guidelines as far back as 2013, where they are pushing for continuous processing and bringing about more efficiency in terms of our ability to produce products at lower costs. They want, of course, things in place, proper processes in place, so we can monitor the process effectively, bring more PAT, process analytical technologies to the fore, so we can ensure that the processes are robust. But ultimately, the driver is to lower manufacturing costs and bring about efficiency. So this is one place where the regulators are actually aligned with this push towards continuous processing. And people who may in manufacturing spaces may think that that's something new and they'll have resistance. Not at all true. Okay, the second reason for considering this is, especially if you're considering a greenfield site. Okay, there's lots of data out there to show that the CapEx of a continuous process is far less, especially if it's dedicated to a particular process, is far less than a greenfield. The greenfield is far less for a continuous process than it is for a batch operation. Sizes of the equipment, number of tanks that are required. Well, you figure you're doing one part of the process at a time, right? So you're batching things, making the batch large, processing, then going to the next step. So even though you can have some marginal overlap, still a very slow process. Daily, and so what we found is that if the process is running continuously, for instance, column sizes can be reduced by as much as 10x because you're doing just continuously more cycles, right? You're not doing this one big batch and running it on a big column, right? So column sizes come down, daily buffer consumption can come down. The hold tanks and surge tanks that are between unit operations go away. And all that QC from all those tanks kind of goes away. And the number of totes required goes down significantly, right? So you have much more usable footprint and a better workflow. So, and of course, it adds up in terms of less FTEs, less waste, less sustainability issues, less energy costs. So overall, it obviously positively affects not only the CapEx by making a smaller facility. Facilities are expensive, but also OpEx as well. And so here's a traditional process, and these have long cycle times. And as I said, you go a step from one process step to another to another. And in terms of process intensification, what are we looking at? We are doing continuous perfusion cell culture, great. And then we might be doing ATF or something, or continuous centrifugation. Then we might be moving to continuous chromatography, some of us are. And then there's, of course, what happens if this is a standard antibody, what happens to the VI step? What happens to the flow-through steps? What happens to UFDF? What happens to formulation, fill, and finish? So we have hold points, and then so these things can be made continuous, they're concatenating these, so they are integrating these various steps, but everyone forgets about buffer management. There's no sense in running a continuous process if you're going to make buffers in batches and run a bucket brigade, right? Where you're having to store lots and lots of totes. So you have long cycle times, and you have, obviously, as a result of these complex operations, your COGS are very high, right? Your cost of goods are very high. And so, the potential impact from going from a batch mode to a fed batch mode to a continuous process could be a 5x reduction in CapEx, and as much as an 8 to 10x reduction in OpEx, right? So really, really major benefits to be had, and we really need to look at carefully and hard at how we can start to incorporate these in our manufacturing facilities. And here's a simple example. Currently, even if you overlap batches and you have a $150 million investment in CapEx, and you're running 8 batches a year, 8-week cycle time, or you overlap these things and are more efficient, you run 10, maybe 12 batches, 70% facility, that's $500 a gram, right? So just keep that in the back of your mind. We are going to come back to that, each of these points. And reason number 5 is, of course, improved workflow. So we design our facilities around the workflow, right? So for instance, we talked about the actual process going back here, right? So these different steps, now we go to the facility design, and, it takes into account this particular process. So here you've got the seed train, the upstream on the bottom in this particular facility. You turn the corner and you have the downstream suites, and you have, the buffer storage area over here. You have column packing here, you have buffer prep here, and you've got the service corridors, right? You have column packing down here. So what happens now if the titer goes up? If the titer goes up, great. Upstream, there's no problem. The downstream, everything is stressed, right? Because these suites are all of a sudden not enough. You have bigger columns, bigger skids. The buffer prep rooms are not big enough because you need more buffers if your column sizes are going up. But for storage, certainly not enough. How many of us have seen totes lined up in these hallways, and people having to stop their runs and pull totes in and remove the spent totes out, right? So very, very common. All these kind of workflow issues and bottlenecks that really slow down the process, cause us to have more FTEs, also cause operational problems and quality problems when you have these issues. And of course, very complex, labor intensive, and costly. Right? So it's not just the COGS don't relate just to amortized capital costs, that you can have a smaller facility if you go continuous, and therefore you have less amortized capital cost, but also the consumables, also the labor, right? So you add all that, and it's a significant effect that you can have on the cost of goods, and of course, your workflow complexity. So we'll just take one example out of the workflow when we talk about complexity. Let's just take the example of making buffers, right? So Bioforum did a study, and they concluded that for making 2,000 liters of buffer, it takes 7 hours with 2 FTEs. Right? So you look at how many chromatography steps are there, what the scale is, and how much buffer do you actually need. Even if you have a continuous process, so down in this particular plan, we have a continuous process where you have in this light blue, you have your process gallery, right? It's like a big ballroom type of operation where you're going closed loop, where you're going from one step to the other. This whole thing in red is your buffer prep. Especially if you're running an intensified process, your titers are high, the amount of buffers that you need are huge, and somebody has to make them, right? So you find that your FTEs in that area go disproportionately as your titers go up, your FTEs and space requirements go up. So, so we have some, I don't know if some of you might be members of NIMBLE, others may not, but for some of us who are members of NIMBLE, which is the National Institute for Innovation and Manufacturing, for their members, they're given a guideline of certain continuous plant design, and we are not privy to show that, but this is a concept very similar to that, where you can have a processing suite essentially down here, right, for a typical antibody going from upstream to, your Chrome 1, Chrome 2, Chrome 3, and intermediate steps in between for a continuous process. And then you could have your individual components of the buffers. I'll say like a monobasic phosphate, a dibasic phosphate, 1 molar as an example, 3 molar salt, or it could be acetic acid, 1 molar, sodium acetate, 1 molar. So the components needed to make the buffer. and the relevant salt or other additives you might need, so those basic chemicals. And then they have a stock buffer blending solution, which can mix 1x or 5x buffers. In order to keep the space down, they propose making 5x buffers and then having chrome skids here with the ability to dilute 5x buffers like that. So that's the space requirement. It reduces the FTEs down considerably from this big size plant that you see on the right here to the smaller size plant here, reduces the number of totes and reduces the space requirement, right? So it reduces the totes, reduces electricity, utilities, people, complexity, all that. And while we talked about costs, in these days, in this day and age of sustainability, not reducing the number of plastic totes by 5x is a big deal, right? So by simply going continuous, you can reduce that. You can reduce the electricity usage and your utility costs and waste treatment. All that makes for a more environmental friendly and environmentally responsible plant that we can all be proud of in terms of designing something for the future, right? So those are all the 7 reasons why we would want to go and consider continuous processing, whether you do it incrementally in each of your steps and move down from the beginning to the end, or you take particular sections of it, or if you're doing a greenfield, doing the whole thing and making connected process. And how can Sepigen help with this? So Sepigen has developed a whole suite of continuous process systems, whether that is a continuous system, with a standard sort of piping or single use, right? So we have both, and we have everything from the bench scale to large scale continuous processing. And so you can see here on the left is a single use continuous 3-column system that can work with 50 to 250 liter perfusion bioreactors. In the middle, you've got a continuous system that can work with over 1,000 liter perfusion bioreactors. So if you've got continuous processing going on in cell culture, if you don't, and you still have very large batches, there's no reason. The downstream is where the main cost of your process is. So there's no reason you can't have an upstream larger tank and process it continuously by having continuous processing downstream, as long as your product is stable and can be kept in storage, right? Then you can have multiple cycles and continuously process. And then here on the right, we've taken this one step further, and we've created a 3-column continuous system, but integrated it in line. So it's not like a separate machine, but we've integrated it in line where you can just use stock chemicals and make concentrated chemicals. Like I was saying, a 1 molar acetic acid, a 1 molar sodium acetate, 3 molar salt, water, and you can make 0.05 for you call up your equilibration buffer, and you can just make 0.05 molar acetic acid or wash buffer with maybe 40 millisiemens or 0.4 molar salt as part of that buffer, your wash buffer. So the continuous processing and continuous buffer making are all integrated into one machine. And as you see down in the P&ID here, in the orange, you can see the load being loaded onto one column, and it's running in overload mode, so it's going on to the second column, whereas the first column, which is pre-saturated, has these buffer on demand, whether it's equilibration, wash, elution buffers, all being made from their stock concentrates and provided to this column. And then these columns go around in a round robin musical chairs or musical columns. So you can continuously run your harvest while you're also doing elution of one column, column 1, column 2, column 3, like that. And we can do it with inline buffer dilution, can do it without inline buffer conditioning, or without, or inline dilution, whatever people want. And here's another example of the bench scale system where that is being done. In fact, we have automated an entire antibody downstream process. So coming from clarified harvest, we have what we call a capture skid, where we have, in this case, a 2-column system, running protein A columns, running the harvest continuously, and washing and eluting from the stock chemicals. So while buffers are being made for these in line on demand. And then going through the VI step where there's a low pH hold, and then a second skid, which is a flow-through skid, essentially a straight-through process, where the pH is adjusted in line by the skid itself, goes through an AEX column. The salinity is adjusted in line, just continuously. There's no hold tank or anything. And then goes through the HIC column, goes through a nanofilter and out. So between these two skids, which is we call a fusion elite and a fusion continuous capture and a continuous flow through, the entire process is done. Okay, so here are pictures of that. Excuse me. And the PNIDs of such a system where you have, the load here going to either column 1 or column 2, and then this is your, buffer making part of the skid, where you have the water pump, the acid pump, the base pump, and the salt pump, all running at different ratios. You don't have to set the ratios. You just set the molarity, the pH, and conductivity in the program, and the buffers are made, and they automatically switch from, as you load, your first column gets saturated, moves to the second column, while the first column goes through the wash, elution, regen, and equilibration cycle, and then they keep flipping. So that's the buffer maker, right? That's the harvest. See the column 1, column 2. And then similarly, we have the flow-through system where you have the AEX column there, the HIC column. Some cases we have a CEX column. And so we've done multiple lines of this. This is a company for which we've done, all three, the capture, the AEX, the CEX, and this is on a high titer 2,000 liter perfusion line on the left here. And so there are 2 parallel lines that they have for this facility, running capture for an antibody processing line, right? Capture, AEX, and CEX. By the way, we can do in the CEX, they're doing gradients. So it's not like you don't have the ability to do gradients and do buffer mixing, all that, inline buffer blending, all at the same time. So essentially, what this enables one to do is do 2 functions in one, right? So whereas you might have heard of continuous processing systems, a lot of the reason why these have not been adopted is because they have to make buffers in batches. And while there are separate machines to do that, they still have to make those buffers, put them in totes, transport them somewhere, move out the empty buffers, move in the fresh buffers, or if there's level sensors in the tanks, then those can automatically turn on the buffer making system. And you have to wait for it to equalize, and then stop the process until those are filled, etc. So there's a lot of complications around that. We've got all that in one neat package here, where in this system you can do continuous chrom with inline stock buffer blending, and that is the equivalent of these two machines. So now you have, really, it frees you up. You're looking at removing the blocks, so it frees you up to adopt continuous processing and manufacturing without a lot of hassle. And so here is the PNID for actually the operating software interface for that machine, where you have the harvest pump here on the top, goes through a pre-column, a switching pre-column filter, bubble trap, goes through column one, through all the bank of sensors, UV conductivity, pH, goes and is running an overload, goes on to the second column, while the first column, which is saturated, is then goes into the mode where it's doing washing and equilibration and regeneration, things like that, from the same set of concentrates. So it's the same, it's the same, let's say, an acetate concentrate that you have hooked up, right, or connected, which is 1 molar sodium acetate, 1 molar acetic acid. But you just tell the machine, okay, I want 0.05 molar acetate, and I want 20 millisiemens, whatever it is, 0.1 molar salt. And the system's pumps will run at the right ratio to give you that molarity, that pH, and that conductivity. And when the buffer is outside that range, you have a process tolerance alarm where that gets ejected, and then it comes back online when it's within the range and goes into the column. Very convenient, very transparent to the user, and you can continuously run your process. You have the usual event logs. You can make recipes. You have a chromatogram where you can look at all the trends.
Run your
So
buffer
I'm going to
side,
show you.
and you can see it's
I'm
in the
going to
blue
show
color.
you a
Once
little
you
bit
finish
video.
your manual run, you just stop it like this, and it will save all the event logs that you can see here, all the alarm logs, and all the chromatogram will be wouldn't go through it today, but I will show you one of the methods that I will running today, which has two unique features, which is a conductivity set point and pH set point. So this is actually what is unique about this system. Whatever you have in the solution concentration, whatever you have in your pH, whatever you have in your conductivity, the system has the capability of doing this kind of blending to reaching to your conductivity set point that you would like to reach and pH set point that you would like to achieve without any interaction from you. You just give the order to the system and the system will do it for you. So for this method I created, we will have a conductivity for 20 millisiemens out of a concentrated solution of 3 molar sodium chloride, which is approximately 200 millisiemens, and we will have a buffer blending between sodium phosphate mono, basic and dibasic at a concentration of 0.5 molar each, and we would like to have a blending giving us a 6.3 pH. So the methods that I created, we can review it together very quick. So as you can see here, it's like an Excel based thing. So here you can type a label for your step. You can choose a flow set point, whatever the liters you would like to have, and a conductivity set point, pH set point, and which inlet you're gonna use. So we have a dedicated bump for each of what I'm talking about. So we have a dedicated bump for the conductivity, which is called bump A. So the system is already know that anything coming from bump A will be for a salt, and bump B is dedicated for an acid, and bump C is dedicated for a base. So whatever the system would like to blend for you to reach out to the set point, it's a random percentage, just
I'm just going to step through it quickly, and if somebody is interested,
you can see
we'll
here,
be putting
this is the
these
first step, just to initiating
online,
the
so you'll
system
be
and
able to
prime it
view
with
it.
bump W, bump B, and bump C. I just create it for 2 minutes. I just can skip it right now and go through my main step, which is step number 2, that has a conductivity set point of 20 and the B.
So anyways, you got the sense. obviously, in deference to all of you, we want to keep to our time here that I promised you, but you get a sense. That was one of our scientists, Ibrahim, who's one of our application scientists, talking about the machine and its ability to be very easily programmed, so you can run continuously and have the buffers be made continuously. You don't have to set ratios of different pumps or flow rates or anything like that. It all does all of that behind the scenes, right? And then the result from something like this is here, for instance, is it's a 200 millimolar salt that we said was 10 millisiemens, achieved in just like 20 seconds. And here, 40 millisiemens is the next wash step. Anything that's outside that envelope, operating envelope, obviously like this part of the peak goes to waste. And uh, while these equilibration and wash buffers are changing, the pH might be changing as well. So pH here, for instance, is going from 7.2 to 3.5. And again, those transitions happen in approximately a minute, right? So that's about the level, given the whole up volume in the system, if you were switching from one buffer to another, that's what would be essentially going to waste, which is what happens in this particular case. And when you hit the stable point, then the buffer goes right to the column. And so in doing this, we looked at the uh, footprint from uh, earlier, and that was this particular, what we were calling a Gen 1 process. What the standard batch process is a Gen 0, and this is a Gen 1 continuous process. And with what I just showed you with those machines, you can eliminate even these buffer making machines and all these whole tanks over here having 5x concentrates, because you can just put your stock chemicals, these chemicals over here, move them right to the front against these skids, and you can go ahead and just do your continuous chromatography with those stock chemical solutions, right? And so it reduces the FTEs, reduces the footprint even further, and reduces the cost. And so just going from like a Gen 1 continuous plant to what we are doing and calling a Gen 2, in this particular model for this plant, we've reduced the capex from 13 million to about 13.6 million to 7.5 million. So that's over a $6 million, almost a 50% reduction in capex. Not to talk about the number of stock buffer solutions or whole tanks that you would need. For instance, here, this is for a continuous process, by the way. You have 14 whole vessels, right? We are down to 4. So look at the impact that we have on sustainability, right? Significant. We have almost 30% lower. And then and we don't need all that space again. So facility size is reduced, capex is reduced, and there's sustainability enhancement. And of course, we've simplified the process, right? So as we've continued, if we can do in the same skid, we can do continuous capture and VI, and the next skid we can do flow through and inline buffer blending. The whole buffer blending part goes away, and this process becomes more simplified and more amenable to continuous processing, right? And then you can see that from a batch process to continuous integrated process, the whole cycle time is reduced to 3 to 4 weeks. And the impact of that is if your cycle time for the same plant is reduced, instead of making 8 or 10 batches, you could be making, your cycle time's 2 weeks, you can make 24 batches for the same output, fixed expenses of people, as well as facilities, your costs can come down dramatically. And in our model, it comes down to 130, from $500 to $130 a gram, right? So you're looking at 4x improvement in plant output because you're making more batches, in that sort of semi-continuous operation, more batches a year, and you're amortizing your costs over more batches, and then the cost of the per dose also, per cost per gram also comes down, right? And there's just more data showing how effective this buffer making continuous systems are. And the nice thing about it is that even if the input chemical concentrations are different, what gets delivered to the point of use is always the same. So if instead of having 200 millisiemens salt, we had 175 millisiemens per centimeter salt, right? We had more or less, you can see the end concentration that comes out that's delivered to the column is always the same. So even if there's variability in how that was put together, how it was measured, the point of use, you always get something that's reliable. So I think you're lowering the complexity also increases the quality of in-process quality, right, of the buffers that are being made. and therefore, by corollary, the kind of product that you're making. So I'm going to summarize now that we are talking here about 7 economic, operational, and sustainability reasons to go with continuous chromatography and preferably integrated with inline buffer blending, like we've shown you. And those are increased output, as we just showed you. You can do more batches per year because your cycle times have come down. CapEx reduction, right? Because your facilities are smaller. And of course, reduce facility footprint, reduce COGS, reduce cycle times. And if your process is more simplified, doesn't have so many hold steps, and having to make buffers, things like that, you're reducing the workflow bottlenecks. And of course, you're improving sustainability, as we just discussed, with reduction of chemicals, smaller footprint, smaller size of equipment, smaller, less disposables, like that. But just about us, if this is a direction you are choosing to go in or considering, look us up. We do a lot of customization downstream. We recognize that one solution doesn't fit all, one size doesn't fit all. People's plants are different, their control strategies, their or if it's a brownfield or retrofit, we have to conform to whatever that your plant's requirements are. And we have project management people here. We've got world-class engineering. And so we can design something that's a better fit for you, as opposed to you're picking something which might be standard and off the shelf, which may or may not work for you. And we go through the whole project plan from preliminary design, P&IDs, solid modeling, the whole DQ process. So we go through the design process, the whole DQ, FDS, drawing reviews, implementation, FAT, SAT, and then eventually IOQs. And then if you have a DCS system, being able to talk to upstream and downstream, if you have a continuous system, being able to talk, whether it's through Profinet or other means, to upstream or downstream equipment is important. You may need to talk with the DCS system through OPC UA. So we provide those facilities, and our software team can work with your team to ensure that. And similarly, if you're on a network and you have to the network authenticates getting onto the system and having certain privileges, we support that as well, right? And so we do a lot of our own custom manufacturing for these things. A lot of parts are not available. We've invented them. We make them here. We're looking at single use. We have our own clean rooms. We have our design team here. We have manufacturing capabilities, custom manufacturing capabilities, 3D printing like that. And at the end of the day, we work with you and we deliver what we promise. So that's all. It's 9:15. I had promised you this would be 45 minutes. And so if you have any questions, you're welcome to ask them. I'll put them in the chat and maybe Sanjit or somebody can ask loudly for you. And if not, I'll wait a couple of minutes for that. If anyone puts up any questions. I don't see anything. So with that, we will call it. I wanted to really thank you for your participation, for being here this morning. And I really hope that you got something of value out of this that I had promised you. And should you be interested in this or want to discuss your situation privately, send us an email or call us, and we'd be happy to organize to meet with you or your team and discuss this offline separately. Again, thank you very much, and I wish you a good day or a good evening, wherever you may be. Bye-bye.